Hey guys, tonight we drift far beyond your own galaxy, past the warm glow of familiar constellations, out into the faint cold spaces between the stars. You find yourself surrounded by something that isn't exactly empty, even though it looks like nothing at first glance. There's a haze here, a faint shimmer like dust caught in a beam of light, only stretched across dozens of light years. This is the interstellar medium, clouds of gas and dust, barely noticeable to the eye, yet it's here that the seeds of stars lie waiting. You probably won't survive this. No oxygen, no heating, and definitely no coffee shop within a few trillion kilometers. But that's okay. You're just here to watch. So before you get comfortable, take a moment to like the video and subscribe. But only if you genuinely enjoy what I do here. Post your location and local time in the comments so I can see just how far this little stargazing trip reaches. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. The cold is ancient here, the kind that seeps through bone. Well, if you still had bones in this imaginary drift. You feel the slowness of space itself. The hydrogen atoms in this cloud move lazily, so rarely bumping into each other that you could wait 1,000 years and not see a single collision. Yet these faint, scattered particles are the raw ingredients for a star. Astronomers call this a molecular cloud or sometimes a stellar nursery, and this one stretches across hundreds of light years, so enormous you could lose an entire solar system in it without a ripple. If you squint, well, squint in the metaphorical sense, you notice that not all of the cloud is equally dense. There are knots here and there, slightly darker against the dim starlight behind them. Historians still argue whether ancient sky watchers without telescopes could spot the most massive of these dark patches with the naked eye. You imagine some long ago observer noting a smudge in the Milky Way, unaware they were looking at the first page of a star's biography. Your slow drift takes you into one of these denser regions. It's still unimaginably thin compared to air back home, but here, gravity is starting to get ideas. Every atom's feeble pull adds up over thousands of years, coaxing its neighbors closer. You sense the faintest tug on yourself, like leaning ever so slightly downhill. It's not dramatic, more like being gently herded by the universe toward a destination you can't yet see. Occasionally, a cosmic tourist in the form of a rogue particle zips past you, traveling absurdly fast, like a late commuter in the world's emptiest subway station. Some of them carry energy from distant explosions, tiny messengers reminding you that out here, violence and beauty often happen side by side. You think of them like cosmic postcards. Wish you were here, exploded 7,000 years ago. Far away, a young star that formed eons before your visit sends a weak light that filters through the dust. It's not bright enough to warm you, but it does paint faint streaks of gold across the gray-blue mist. In the silence, you realize this isn't just emptiness. It's the quiet before something enormous happens. If the galaxy had a bedtime routine, this would be the part where it brushes its teeth and pulls up the blanket, settling in before the alarm goes off in a few million years. As you glide deeper, the darkness thickens. The gas here is so dense, again, speaking relatively, that even the light from background stars can't break through. This is the quiet zone, the prenatal stage of stellar life. Observers on Earth see regions like this in silhouette, dark blotches against the glittering Milky Way. You, on the other hand, are inside it, and that's a different experience entirely. It's like being in a fog, where the fog is made of hydrogen, helium, and a sprinkling of carbon-based dust grains. Tiny bits of what will someday become planets, maybe even people. The cold intensifies, hovering just a few degrees above absolute zero. Your breath would freeze instantly if you could breathe here, but in this cold, the atoms cling to each other, forming simple molecules. Water, carbon monoxide, ammonia. They're all floating here in quantities so small you could gather A swimming pool's worth only by scooping for centuries. Still, they matter. Someday, these molecules will be baked into the heart of a star, then flung out into space again to seed new worlds. You spot something odd, a streak of slightly warmer gas winding through the cloud like a lazy river. Astronomers think these can happen when shock waves from a distant supernova ripple through the region, nudging particles closer together. It's a strange thought, a star's violent death in one corner of the galaxy, setting the stage for a star's gentle birth in another. Life, death, rebirth. Space isn't sentimental, but it's consistent, and still, you drift. The stars beyond the cloud fade from sight entirely now, hidden behind the thickening curtain of dust. There's only the faint glow of infrared light, heat. Too dim for your eyes to see, but you feel it in the background, like the memory of a campfire long after it's gone out. Somewhere ahead, the gas is about to reach a tipping point. Gravity will pull harder, particles will move faster, and the quiet will give way to a slow, steady contraction. But for now, here in this vast, cold darkness, time has no urgency. You float in a place where 1,000,000 years is just the warm-up. And in that sense, you're perfectly safe here, unless you count the total lack of oxygen, sunlight, or Netflix. The first hints of movement are so subtle, you almost think you imagined them. A gentle current passes you, like a lazy exhale in the darkness. It's gravity, working so patiently you'd never notice it unless you stayed for centuries. Well, which you apparently are. Every tiny tug between particles is starting to add up, pulling this cold gas into tighter and tighter knots. You feel yourself sliding along with it, like a marble in the shallowest part of a bowl. Here in the denser patches, collisions between atoms happen more often, though more often, in astronomical terms, still means a very patient game of bumper cars. Each collision gives off a faint whisper of heat, barely enough to notice, but enough to change the math. Warmer particles jiggle faster, bumping into each other more often, generating more heat in a slow-motion chain reaction. Astronomers call this stage the gravitational collapse, and without it, stars simply wouldn't exist. But there's no drama yet, no blazing light or triumphant music cue. Just an immense, steady tightening, like the galaxy quietly tying a knot in its own hair. Historians still argue whether the earliest human civilizations, those who carefully mapped the stars, imagined these hidden births behind the patterns they saw. After all, they only had the night sky as it was. The invisible motions were ours to uncover much later. As you drift deeper into one of these contracting pockets, you notice the cloud's texture has changed. It's lumpier now, not the smooth, pale mist you floated through before. Each lump is a region where gravity is winning the tug-of-war. These clumps might look unremarkable, but they're future headlines in the universe's news feed. Stars to be, each slowly forming its own destiny. Occasionally, a small shock wave from outside, a brush with another cloud, or a distant explosion sends a shiver through the gas. The ripples travel slowly, nudging matter together in ways gravity appreciates. You're reminded of a crowd in a lazy queue that suddenly shuffles forward, everyone inching just a little closer to the goal. If there's a cosmic customer service desk at the end of this line, it's a blazing ball of plasma. As the density increases, so does the heat. You feel the faintest warmth seep into your skin, imaginary skin in this case, but it's enough to make you realize something important. Space isn't always cold. In these dense pockets, energy has fewer escape routes. When particles bump together now, the heat they generate sticks around instead of radiating away instantly. It's like putting a blanket over a lukewarm cup of tea. The warmth lingers, slowly building. You catch sight of a swirl nearby, a whirlpool of gas rotating ever so gently. Rotation happens because nothing in the universe can quite stay perfectly still. Even the tiniest motion gets amplified when you compress something this huge. That swirl will eventually flatten into a disk around the forming star, and from that disk, planets might one day take shape. But that's a story for later. Another oddity drifts into view. A thin streak of darker dust within the brighter cloud, almost like a vein of shadow. Some astronomers think these filaments guide gas into the forming star, funneling material inward. Others suspect they're the remains of older structures, shredded and reformed by passing shock waves. Either way, they give the cloud a strangely organic look, like roots feeding a growing seed. The pull of gravity here isn't something you can fight, even if you wanted to. Slowly, steadily, you're being carried inward. You imagine what it would be like if this were audible. A faint, unending sigh from all directions, urging you toward the center. No one hears it, of course, but you can almost feel it in your bones. Over countless years, the collapse accelerates. The clump you're in shrinks, the gas inside getting denser, the heat rising degree by degree. The outside world grows more, distant, literally. Light from beyond struggles to push through the thickening wall of gas and dust. You're in a cocoon now, sealed off from the rest of the universe. And yet, despite this slow but unstoppable transformation, it still feels peaceful. There's no violent tearing, no explosions, just an invisible pressure knitting the cloud tighter. This is nature's patience in its purest form. If you could fast forward, you'd see a sphere taking shape in the middle of the clump, a place where the density is so high that the gas can't help but heat itself into something new. That sphere is the next chapter of this story, the shy beginning of a star. Before you leave this moment, you take in one last look at the collapsing cloud around you. The swirls, the filaments, the faint ripples from far-off events, they all work together, slowly sculpting a future light that will one day pierce this darkness. And for now, you're right here in the middle of it, weightless and patient, waiting with the universe for the first sign of a spark. The darkness around you feels heavier now, not in any emotional way, though if you were the poetic type, you could call it that, but literally heavier. The gas and dust are squeezing tighter into the center, and you're along for the ride. You can't feel acceleration here. Space doesn't work like a roller coaster. It's more like you've been drifting for so long that you suddenly realize you're closer to something than you were before, and you didn't even notice the approach. In this deep, insulated pocket of the collapsing cloud, the central knot is becoming what astronomers call a protostar, the universe's equivalent of a newborn still wrapped in blankets. The core temperature has been creeping upward, powered only by gravitational energy. Every time particles tumble inward, they convert a bit of that falling motion into heat. Think of it as the world's slowest bonfire, built not with logs but with hydrogen atoms, each one contributing the tiniest spark. And here's a quirky bit. Despite being surrounded by gas, a protostar is often invisible to our eyes. All that dust in the cocoon absorbs visible light. You could be a few light days away and never spot it without infrared detectors. That's why early astronomers had no clue these things were hiding all over the galaxy. They were like shy teenagers refusing to come out of their rooms until they'd figured themselves out. The air, well, air, if we're being generous, is much warmer now. You can't breathe it, you can't touch it, but you can imagine it pressing lightly against your cheeks in a constant, invisible tide. The density is thousands of times greater than when you first entered the cloud. In human terms, it's still vacuum, but in cosmic terms, it's practically elbow to elbow in here. Historians still argue whether the first modern astronomers to theorize about protostars truly grasped how long these phases take. The whole process can stretch over hundreds of thousands of years, depending on the star's future size. Your human brain, raised on quick coffee breaks and 2-day shipping, can't help but find that absurdly slow. Here, even the exciting moments happen on a time scale that would make continental drift tap its foot impatiently. Occasionally, a gust of turbulence shakes the region, stirring the dust like a slow-motion snow globe. Turbulence isn't always welcome. It can slow down the collapse, but in just the right dose it mixes the gas, spreading heat and elements more evenly. You drift past a wave of carbon monoxide molecules, not the friendliest stuff for human lungs, but essential markers for scientists trying to map star birth from far away. Your eyes, or whatever passes for them in this thought experiment, adjust to the faintest glow in the distance. It's not fusion yet, but the heating core of the protostar is beginning to radiate in the infrared. If you could translate that warmth into a visible color, it would be the deep red of embers under ash. Still, the surrounding dust keeps it hidden, like a secret only you and the molecules in here are in on. Every so often, you spot narrow jets of material shooting out from the poles of the forming star. They stream away in nearly straight lines, carving paths through the surrounding cloud. Astronomers call these Herbig-Haro objects. Yes, it's a name that sounds more like a law firm than a cosmic event. But they're the result of magnetic fields channeling material outward. They're one of the first signs that the protostar is not just collapsing, but also starting to organize itself, shaping its surroundings in quiet, forceful ways. Meanwhile, the rotation you noticed earlier is more obvious now. The surrounding, gas and dust are flattening into a disk, spinning gently around the central glow. It's the first whisper of a solar system to be. That's where future planets, asteroids, and comets will emerge. But you file that thought away for later chapters. It's warmer still, and for the first time since you started this cosmic drift, there's a faint sense of anticipation. You're standing, floating, at the edge of something irreversible. Once the temperature in the core crosses a certain threshold, fusion will ignite, and there will be no going back. That moment is still ahead, but the signs are clear. The protostar is feeding, growing heavier, drawing in more and more of its birth cloud. For now, you hover in the cocoon, surrounded by whisper-thin spirals of dust and glowing knots of gas. Outside this dense bubble, the original molecular cloud is still vast and quiet, unaware, or perhaps entirely aware, that one of its seeds is almost ready to blaze into life. And you, the very patient observer, are here to watch the last moments, before first light. The airless darkness around you holds a new tension, like the room just before someone flips on the lights. The protostar at the center of this cocoon is nearing a milestone it's been crawling toward for hundreds of thousands of years. You can feel it, well, feel in that dreamy ASMR kind of way, as the heat in the core ratchets up degree by degree. It's a race between temperature and pressure now, though calling it a race when it takes millennia might be overselling the urgency. Inside that growing sphere, gravity is still squeezing every particle inward. The atoms, mostly hydrogen, are crammed so close together that their mutual repulsion is on the verge of breaking. When the core reaches roughly 10 million degrees Celsius, yes, that's 10 million, those hydrogen nuclei will finally start fusing into helium. And when that happens, you'll witness the cosmic equivalent of a baby's first cry, first light. It's worth noting that first light isn't as theatrical here as it sounds. There's no champagne bottle breaking against the hull, no "Welcome to the Galaxy" gift basket. The glow will simply seep outward, wave after wave of energy created by nuclear fusion in the star's heart. And here's the quirky bit. Those photons will take thousands, sometimes millions of years just to travel from the core to the surface, bumping around like lost tourists in a very crowded subway. By the time the light finally escapes into space, the event that made it is ancient history. Historians still argue whether we should think of this as the true birth of a star or just the start of its more public life. After all, the protostar's been quietly existing for a long time before fusion begins. But in the grand family photo album of the cosmos, this is the page where the baby pictures stop being grainy ultrasound blobs and start looking like a recognizable face. You hover now just beyond the dusty veil, watching as the surrounding cloud starts to thin. Radiation from the newborn star is pushing back the gas and dust, a slow-motion clearing of the throat. Some of that material will escape entirely, swept away into the wider galaxy, while the rest might hang around to help build planets later. On from your vantage point, you catch a faint shimmer, like the first warm glow of a lamp under a thick blanket. It's not dazzling yet, but it has a presence you can't ignore. The Herbig Haro jets you saw earlier are still streaming away from the poles, but now they're lit faintly from within, their edges tinged with the newborn star's radiation. The rotation in the disk around the star is picking up too. You can almost imagine the future here. Clumps in the disk cooling, sticking together, spinning into orbits. The neighborhood is slowly becoming more organized, though slowly is, again, a galaxy's idea of the word. If you measured it in human terms, this phase would take longer than all of recorded history, plus the time it takes to read the fine print on a phone contract. Occasionally, a piece of the birth cloud drifts past you, caught in the outgoing flow of stellar wind. These are streams of charged particles now racing outward from the star's surface. They'll keep blowing for the rest of its life, carrying whispers of its chemistry into space. In a distant future, those particles might drift across light years, get swept into a different cloud, and help build another star. The universe recycles with ruthless efficiency. The warmth here has changed from the gentle seep of gravitational energy to the steady pulse of fusion. If you could hold your hands out, which again, you can't, they'd feel the difference. This heat isn't the slow compression of a gas cloud anymore. It's the constant, roaring furnace of hydrogen atoms fusing into helium, releasing enough energy to keep this star shining for billions of years. And yet, the scene remains strangely tranquil. You're watching something unimaginably powerful, but it's wrapped in such vast silence that you can almost forget it's happening. The light is stronger now, beginning to burn through the veil. You catch glimpses of space beyond. Background. Stars winking in through thinner patches of dust. The cocoon is opening. The star's first chapter as a main sequence object is about to begin. Soon, it will settle into the long, stable stretch of its life, burning hydrogen at a measured pace. For now, though, it's just taking its first deep breath, exhaling energy into the void for the first time. And you're right here, floating in the gentle warmth of its earliest glow. The cocoon is gone now. You're drifting in open space again. Though not the cold emptiness you remember from before, there's a new warmth here, a steady hum that wasn't present when you first arrived. The star, now fully in its main sequence stage, shines at the center of its clearing. No longer shy, no longer hidden. You can actually see it now, its light spilling across the remnants of its birth cloud like a lantern catching the edges of a fog. This is the long, steady part of a star's life. For the next few billion years, give or take depending on its size, this star will burn hydrogen into helium with almost obsessive regularity. Imagine a campfire so perfectly maintained that every log burns at exactly the same rate, never flaring up, never dying down. It's the cosmic version of a boring but stable desk job. Nothing flashy, but it pays the bills and keeps the lights on. The balance that keeps this going is called hydrostatic equilibrium. Gravity pulls inward, trying to crush the star into itself, while the energy from fusion pushes outward, resisting the collapse. It's like the world's longest, most perfectly balanced game of tug-of-war, with no winner and no loser. If either side gets ahead, the star changes. But here in the main sequence, the match stays even. Historians still argue whether this stability is the true prime of a star's life or just the most photogenic phase. From a purely scientific perspective, it's where stars spend the majority of their time. From a poetic one, it's the stretch when a star quietly supports everything that will form around it, planets, moons, comets, without demanding much attention. The surrounding space is changing too. The rotating disk of gas and dust around the star is thinning. Some of it is clumping into small bodies, Some is being swept away entirely by the star's wind. You notice faint trails of dust spiraling inward, burning up as they hit the stars. Surface, tiny reminders that even in this calm stage, there's still a slow rain of matter falling in. You drift closer, and the light feels different now. It's not just bright, it's consistent, a steady output that could warm a nearby planet to a comfortable temperature for life. In fact, given enough time, one of those forming clumps in the disk could settle into the right orbit, collect an atmosphere, and maybe, just maybe, end up with oceans and clouds. You can't help but imagine future beings staring up at this star and wondering about their place in the universe, never realizing they're gazing at something you watched come to life. Here's a quirky thing about main sequence stars. They change so slowly that from a human perspective, they're practically frozen in time. If you checked back in 1,000 years, you'd probably find this star looking exactly the same. Even 1,000,000 years would only bring subtle shifts in brightness and size. In that way, stars make excellent long-term companions. They'll never ghost you unexpectedly. Still, even in this apparent stillness, slow processes are at work. Hydrogen in the core is steadily turning into helium, and over time, the buildup of helium changes the star's structure. It will get slightly hotter and slightly larger as it ages, but so gradually you'd need to compare snapshots millions of years apart to notice. Occasionally, you spot tiny flashes near the surface, brief magnetic storms that send arcs of plasma leaping into space. They're like miniature fireworks, gone in minutes, barely a hiccup in the star's routine. If you were sitting on a planet nearby, though, those flares could play havoc with your radio signals or your sunburn. From out here, though, it's serene. The star just glows, steady and unwavering, a perfect metronome in the symphony of the galaxy. The chaos of its birth is over, and the drama of its death is still far ahead. For now, it's just doing its job, shining in every direction, sending its warmth and light into the void. And you're still here, weightless in its glow, watching as billions of years pass in the blink of a cosmic eye. Billions of years slide past like beads on an invisible thread, and you barely notice the change until it becomes impossible to ignore. The star's light, once a clean, constant white gold, begins to take on a richer hue. It's warmer now, not in temperature, but in tone. The way sunlight in late afternoon feels different from midday. It's the first whisper of what's coming. Deep in the core, the math has shifted. Hydrogen, the star's main fuel, is running low, at least in the central regions where fusion is most efficient. For eons, gravity and fusion have been in perfect balance, but now fusion can't keep up. Gravity starts winning tiny victories, compressing the core bit by bit. And here's the strange part. When the core squeezes down, it heats up. That extra heat jump-starts fusion in the shell of hydrogen surrounding the helium core, causing the star's outer layers to expand. You watch, and it's like the star has suddenly discovered vanity. It swells, puffing out its chest as if trying to impress the neighborhood. The surface cools slightly during this expansion, and cooler stars tend to glow redder, so the color deepens, shifting toward a blush that will only grow more dramatic. This is the subgiant phase, the awkward teenage years of a star's life. It's not the compact, energetic youngster it used to be, nor is it the full red giant it's destined to become. Right now, it's stretching into a looser, less stable form, burning fuel in weird places and adjusting to its changing body. If it could talk, it might complain about how none of its old clothes fit anymore. One mainstream fact astronomers love: our own sun will one day go through this phase. Don't panic. One day here means roughly 5 billion years from now. By then, humanity will either be comfortably spread across the galaxy or so gone that the cockroaches have their own space program. A quirky side note: as stars swell in this stage, any nearby planets feel the effects long before they're swallowed. Orbits can shift. Tidal forces can stretch worlds like warm taffy. Imagine waking up one morning to find your year suddenly shorter because your planet's path around the star has shrunk. That's the sort of surprise gift a subgiant hands out. Historians still argue whether this period should be considered the start of a star's decline or simply the next phase of its existence. The word decline makes it sound sad, but there's something undeniably grand about a star throwing off its modest, tightly bound self and ballooning into a showpiece. You could think of it less like getting old and more like finally dressing for the part you were born to play. You drift back a little as the surface layers swell outward. The star's gravity is still strong, but those layers are held more loosely. Now, solar winds strengthen, carrying a steady stream of particles into space. If you could hold out a sail, you'd feel the push, a constant pressure from that glowing giant. In the surrounding space, dust and gas get caught in this expanding wind, scattering like glitter in slow motion. It's beautiful, but it's also a sign that the star is starting to lose mass. Not much yet, just a whisper of what's to come. But every lost particle is a piece of itself, drifting away forever. The light feels different on your face now, even here in the void. It's softer, less like a sharp spotlight and more like the warm wash of a heat lamp. Planets in the habitable zone might actually get toastier than before, their climates shifting in ways that could be delightful or devastating, depending on who's home. You hover there, watching the surface ripple with convection currents, huge loops of hot plasma rising and falling like the breathing of some colossal creature. Beneath that surface, the real drama is building in the helium core, now inert but growing heavier with each shell fusion cycle. The star is changing from the inside out, and you can feel the tension, the way a calm before the storm almost hums in your bones. There's no rushing it. Stars don't do anything quickly unless they're dying spectacularly, and this one still has some slow, graceful swelling ahead of it. But you know the next phase will be unmistakable. This star is going to keep growing until its size alone demands your awe. The swelling doesn't stop. It accelerates. You find yourself drifting farther back, not because you're moving, but because the star's surface is racing toward you. It balloons out, layer after layer, until it no longer resembles the neat sphere it once was. Its glow is now a deep, burnished orange-red, the kind of light you might imagine from a distant campfire that fills the whole sky. The heat you feel here is deceptive. Despite being larger, the surface is actually cooler, only a few thousand degrees compared to its younger, hotter self. But don't get too cozy. Cooler, in stellar terms, still makes it hot enough to vaporize any notion of marshmallows. Its energy output has climbed, not because of temperature, but because of sheer size. The photosphere stretches across a region so massive it could swallow Mercury, Venus, and possibly Earth without even burping. You are now in the presence of a red giant. Inside, the helium core has become like a dense, inert knot about the size of Earth, but with a mass so great you'd weigh tons standing on it. If somehow you could survive standing there, which you can't. Hydrogen fusion still burns furiously in a shell around the core, feeding the expansion and brightening of the outer layers. One mainstream fact: red giants are responsible for enriching the galaxy with elements heavier than helium. Without this phase, there'd be no carbon-based life. The very stuff you're made of, carbon, nitrogen, oxygen, was cooked in the bellies of stars just like this, billions of years ago. You are, in the most literal sense, star stuff wearing headphones. Here's your quirky tidbit for the night. Some red giants pulsate like slow cosmic heartbeats. Their outer layers rhythmically swell and shrink, changing brightness over weeks or months. If you set their light curves to music, you'd get something oddly hypnotic, like the universe's version of a lo-fi chill beat. Astronomers still debate whether our sun will one day engulf Earth entirely or just crisp it to a lifeless rock. The uncertainty comes down to complex models of mass loss versus orbital expansion. Either way, It's not looking great for beachfront property in 5 billion years. You take in the spectacle. The star's surface is mottled with enormous convection. Cells, each so large they could swallow continents whole. Material from deeper layers bubbles up, cools slightly, then sinks back down, creating a rolling, boiling pattern that makes the entire star look like it's in slow, roiling motion. Solar winds are no longer a gentle push, they're a gale. Streams of gas blast outward at speeds of millions of kilometers per hour, shaping the space around the star into a swelling cloud. Dust forms in these winds, catching and scattering the light, giving the surrounding space a faint, smoky glow. If there are planets in the way, they don't stand a chance. The atmospheres of the closer ones strip away. Their surfaces, if they're rocky, might crack and vaporize. Gas giants farther out might lose their upper layers, shrinking into smaller, denser worlds. And any alien life unlucky enough to be on those planets is probably updating its evacuation plan, assuming it hasn't already melted into history. You feel the weight of the star's story pressing in, not just its mass, but its inevitability. Gravity wants the core to collapse, but for now, fusion in the shell keeps pushing back. It's a stalemate, but one that can't last forever. The helium core grows hotter and denser with every passing million years. Inching toward a breaking point you can almost hear in the silence of space. From here, the red giant looks serene, but you know it's a mask. The real drama is in the balance sheets of mass, temperature, and pressure deep inside. The clock is ticking toward something far more violent, a shift that will ignite an entirely new kind of fusion and change the star's fate forever. The tension inside the red giant finally snaps. You feel it before you see it, a deep, silent lurch in the fabric of space, as though the star just took a breath so big it might never exhale. Deep in the heart of this swollen giant, the helium core has reached a critical temperature, about 100 million degrees Kelvin. That's not too hot to touch, that's too hot for atoms to keep their personal space. And just like that, the helium flash begins. For a low to medium mass star, this is no slow burn. It's an almost explosive ignition of helium. Fusion in the degenerate core. Degenerate here, meaning the atoms are so densely packed that quantum pressure, not temperature, keeps them from collapsing. For eons they've resisted, but now they surrender to the heat. Helium nuclei smash together in the triple alpha process, creating carbon and a little oxygen at an astonishing rate. Mainstream fact: this helium flash can release in a matter of minutes the same amount of energy our sun emits over tens of millions of years. Fortunately, or unfortunately for fireworks fans, all this drama happens inside, buried under layers of stellar gas. The outer layers barely notice. There's no visible supernova-like explosion here. Your quirky tidbit: some astronomers like to call this moment stellar puberty, because the star abruptly changes its energy source and settles into a new equilibrium, much like a teenager's voice suddenly dropping an octave. The comparison might be silly, but it fits. The helium flash marks the awkward transition between the chaotic swelling phase and a more stable middle age for the red giant. Scientists still argue whether helium flashes are uniform events or if there's a spectrum of intensities. The debate hinges on computer simulations versus indirect observational evidence. After all, you can't exactly peek inside a star mid-flash without becoming a footnote in a physics textbook titled "People Who Shouldn't Have Tried That." As the helium fusion stabilizes, the core expands slightly, reducing the crushing pressure. This causes the outer layers to contract a bit, and the star's overall size actually decreases. It's still massive, but the red giant now burns helium in its core and hydrogen in a shell around it. You can think of it as a cosmic layer cake, with each layer baking at its own temperature and flavor. The light changes subtly. The once deeper orange glow shifts toward yellow-orange, a sign of the higher surface temperature. If you had a thermometer, that could handle it, without instantly becoming plasma, you'd find the photosphere has warmed by a few hundred degrees. Not enough to look dramatic from here, but enough to alter the star's behavior. From your vantage point, you can see that the pulsations slow. The once wildly heaving outer layers settle into a rhythm, the star's brightness becoming steadier. This horizontal branch phase, astronomers love boring names, can last hundreds of millions of years, depending on the star's mass. Around the star, the cloud of expelled gas continues to drift outward. Some of it will eventually cool and condense into interstellar dust. Billions of years later, that dust might end up in the rings of a planet, the core of a comet, or even the bloodstream of a creature sipping tea somewhere and wondering about the stars. The wind howls less violently now, though still strong enough to carry away a steady stream of material. You imagine riding one of those currents, particles of carbon and oxygen whipped into space at thousands of kilometers per second, destined for places unknown. It's an oddly romantic thought. Pieces of this star will one day travel farther than any spacecraft humanity has built. But you also sense an inevitability here. Helium, though more fuel-rich than hydrogen, won't last forever. Once the core exhausts its helium, the delicate balance will tip again. And when it does, the star's path will diverge, depending on its mass. For now, you float in the quiet aftermath of the flash, feeling the subtle hum of fusion deep below. The red giant has survived its crisis, for the moment, and entered a calmer chapter of its life. You know better than to trust this piece. It's only the eye of the storm. You've been lulled into the star's gentle rhythm, its pulsations now more like the steady breathing of something asleep. But stars don't truly sleep. They just bide their time until the next round of chaos. The helium in the core burns on, steadily forging carbon and oxygen. The triple alpha process hums along like an industrial furnace that never cools, and above it, the hydrogen shell continues to fuse away, adding fresh helium to feed the core. It's like a cosmic two-story house. The upstairs is still busy with construction, while downstairs, the workers are quietly making the foundation denser and heavier. Mainstream fact: carbon and oxygen aren't just random leftovers. They're the backbone elements for life as we know it. Without red giants like this one, your bones, your blood, even the air you're breathing right now would be impossible. You are, in a very literal way, a descendant of some star's final act, your quirky tidbit. A few physicists have compared the layering in a red giant to a giant onion. But unlike your grocery store onion, this one could vaporize your entire solar system if you peeled it. The irony? Peel an actual onion and you'll still end up crying. So, in both cases, it's probably best not to mess with them. Historians, well, astronomers in this case, still argue whether the carbon-to-oxygen ratio in a dying star is fully predictable or if small variations during helium burning can tip the balance in ways our models can't yet capture. It matters because that ratio determines what kind of white dwarf, or in more massive stars, what kind of heavier elements, will result. Tiny shifts can mean the difference between a carbon-rich planetary nebula and one brimming with oxygen. From where you float, you notice subtle changes in the star's color again. The contraction after the helium flash has made the surface slightly hotter, pushing the glow toward a softer yellowish tone. You imagine if your eyes could stretch across centuries, you'd see the light drift through shades the way autumn leaves do. Though here, instead of a few weeks, the transformation would take millions of years. The core, meanwhile, grows heavier and hotter. Helium doesn't last nearly as long as hydrogen did, so this phase is comparatively brief. Think of it as the star's middle-aged homeowner era. It's stable, productive, but constantly aware of the mortgage clock ticking down. The steady fusion keeps the outer layers inflated, but as the helium dwindles, you sense tension building deep inside, like a coiled spring, waiting for the next snap. You drift closer into the faint wind of the star's ongoing mass loss. The particles are fewer than in the earlier red giant stage, but they still sting your imaginary skin like dry sand on a windy beach. Each grain is a fragment of future worlds. You can't help picturing some alien astronomer billions of years from now holding a rock in their six-fingered hand, never knowing it once came from this very star's breath. Then the signs start showing. The helium in the core is running out. You feel the temperature rise sharply again, and the outer layers begin to expand once more, undoing the contraction from the helium flash aftermath. The cycle is repeating, but this time, the outcome will be more dramatic. In low-mass stars, like our sun will one day be, the core never gets hot enough to ignite carbon. Instead, when helium runs out, the star will swell enormously, turning into an even larger, cooler, puffier red giant, sometimes called the asymptotic giant branch stage. For now, you're watching the first hints of that transformation. The light softens back toward red, the surface cools slightly, and the star starts to look more bloated again, as if it's reluctantly going back into its big winter sweater. In the layers above the core, hydrogen and helium shells are now burning, simultaneously creating a complex, unstable balancing act. The result, powerful thermal pulses that can drive off whole swaths of the star's outer atmosphere in slow-motion waves. You imagine these pulses like the bass line at a distant concert, deep, regular thumps that you feel more than hear. Each pulse carries away mass, thinning the star's reserves and thickening the expanding cloud around it. That cloud is starting to look like something that could, given time, become a planetary nebula. There's a strange beauty in the inevitability of it all. The star knows what's coming, at least in the metaphorical way you assign it sentience. It's building toward a farewell performance, not in a blaze of core collapse, but in a gentle, shimmering shedding of everything it's been. And you're here for the front row seat. The pulses come more often now, each one swelling the outer layers before gravity pulls them partway back. You can almost hear the star sigh, the way an old house creaks when it settles in the night. It's a rhythm of expansion and contraction, but each expansion sends a little more of the star drifting away into the surrounding space. Mainstream fact: these thermal pulses on the asymptotic giant branch are some of the most efficient ways for stars to enrich the galaxy with elements heavier than helium. Carbon, nitrogen, and even small amounts of S-process elements, like barium, are lifted from the interior and carried into interstellar space. If you've ever admired the sparkle in a piece of jewelry containing barium glass, you can thank a star in this very stage for it. Your quirky tidbit: astronomers sometimes call the periodic outbursts in this stage stellar burps, which is fitting, because the star is essentially regurgitating bits of its insides. If stars had dinner parties, this would be the point where everyone politely looks away, pretending not to notice. Astrophysicists still argue whether the exact timing and size of these pulses are predictable from first principles, or if chaotic processes deep in the convection zones make each star's life story a little different. That uncertainty means our models of galactic chemical evolution, how all the elements are mixed and redistributed, are still partly educated guesswork. From your vantage point, you notice the star's surroundings getting thicker. The mass it's losing doesn't just vanish, it builds into a dusty cocoon. Over millennia, this shroud will block more and more of the star's visible light, letting only infrared leak through. If you had an infrared camera, the star would blaze even brighter than before, like an ember hidden inside smoke. You drift through that dust, feeling the static from tiny grains brushing past. Some are rich in carbon compounds, others in silicates. These are the seeds of future planets, comets, and maybe even the foundations of life. You remember that not all life needs a blue sky and an ocean. Some worlds might breathe methane under orange clouds and still owe their existence to this star's shed skin. Deeper inside, the helium shell flickers. Its fuel is dwindling fast. Each flicker is like a skipped heartbeat in the cosmic tempo, a sign the steady fusion dance is about to end. The core itself, composed mostly of carbon and oxygen, keeps contracting under its own gravity. No amount of outer shell burning can stop that slow squeeze. At this stage, you're witnessing the star's identity split in two. The outer atmosphere is chaotic, turbulent, and in constant motion. The inner core is silent, heavy, and locked in a slow march toward its final form. There's no drama in the core's contraction, no flashing lights or sudden roars, just a relentless tightening, like a knot pulled by invisible hands. One of the pulses hits harder than the rest. It pushes a massive shell of gas outward, far, enough that in a few thousand years it will form a luminous halo. You watch it ripple away, faintly lit from behind. The symmetry is eerie, like a perfectly round smoke ring, but big enough to swallow our entire solar system. The star looks a little smaller afterward, as if that outburst cost it more than just mass. Its surface temperature creeps up slightly again, but the overall brightness dips. This is the tug-of-war phase. Each pulse erodes the star's strength, and between pulses, the shells of hydrogen and helium fight to keep things running. If you could compress millions of years into a few seconds, you'd see the star's brightness and size pulsing like a slow strobe. Over time, the intervals shrink, the outbursts grow, and the atmosphere grows thinner. Eventually, one last series of pulses will strip the star entirely bare, exposing the hot, dense core that has been hidden for eons. And when that happens, the surrounding cocoon will blaze into a planetary nebula, though it has nothing to do with planets. It's just an astronomer's old naming quirk from when telescopes were new and fuzzy green disks looked vaguely like distant worlds. You hover at the edge of this dusty bubble, knowing that soon you'll see that final transformation. It won't be violent in the supernova sense, no cataclysmic shattering, but it will be luminous, colorful, and brief. A swan song before the star settles into its quiet old age. The cocoon is thinning, but only in patches, letting shafts of light leak out like lantern beams through a tattered tent. Each shaft is tinted slightly differently, amber where the dust is rich in carbon, pale green where ionized oxygen gas takes over. You drift closer, and the light is soft enough to make you think of candle glow on an old library wall. Except these candles could scorch entire planets to ash without even trying. Mainstream fact: this is the onset of the planetary nebula phase, when the dying star's outer layers, expelled in the last round of thermal pulses, are lit from within by ultraviolet radiation streaming from the now exposed core. Those photons ionize the surrounding gas, making it glow in intricate colors. Your quirky tidbit: early astronomers peering through modest 18th century telescopes thought these glowing shells looked like distant worlds. So, planetary nebula stuck as a name, even though they're basically cosmic neon signs, not planets at all. Imagine discovering a disco light and insisting it must be a marble rolling through space. Astronomers still argue whether all stars in this mass range go through a full classic planetary nebula stage, or if some skip straight to becoming a white dwarf without much of a show. It might depend on how fast the core heats up versus how quickly the ejected material disperses, meaning this glowing cocoon you're in might be a cosmic luxury, not a guaranteed finale. The core itself, now stripped bare, is dazzlingly hot, over 100,000 degrees Kelvin. Its brightness shifts to shorter wavelengths, pouring out ultraviolet light that your human eyes couldn't see unaided. In your mind, it's like the star has changed fashion entirely, from the loose, colorful robes of its giant phase to a bare, white-hot minimalism. As you float through the nebula, the gas forms filaments and knots around you, sculpted by the star's earlier pulses. Some of the clumps are denser than others, shielding parts of the gas behind them from the ionizing light. This patchwork of light and shadow creates delicate lace patterns, as though the star's last breath was filtered through embroidery. Farther, From the core, the nebula's glow fades into darkness. Here, dust grains are already drifting into the general interstellar medium. They'll wander for millions of years until gravity from some future star-forming cloud pulls them into a new cycle. It's strange to think the atoms brushing past you now could one day be part of an alien's morning coffee mug. The whole structure is expanding, slowly by your personal clock, but at tens of kilometers per second by cosmic standards. You notice how the light changes subtly as the shell grows, its density dropping, the colors shifting. The nebula is a fleeting thing, destined to fade within maybe 20,000 years, a cosmic blink compared to the billions of years the star spent in its stable prime. The core at the center is already on its way to becoming a white dwarf, the final state for most stars like this. There's no more fusion going on inside. It's just cooling now, radiating away the last of its heat like a stone taken from a fire. But that cooling process will take longer than the age of human civilization. Many times over, you glance back toward the denser inner shell. In your mind's eye, you overlay the star's history, the cool hydrogen clouds of its birth, the turbulent youth of main sequence life, the swelling giant years, and now this, its delicate, luminous exhalation. It's hard to believe this. Glowing beauty is, in astronomical terms, nothing more than an afterimage. A particularly dense clump drifts by, and for a moment it blocks the core entirely, throwing you into shadow. Then you drift out of its shade, and the ultraviolet glare floods your senses again. The contrast is startling, like stepping from a moonless forest into a sunlit snowfield. You can feel the last big shift coming. As the nebula expands and thins, the light will weaken. Eventually, the gases will become too spread out to glow brightly, and the white dwarf will be left alone, cooling in the dark. But before that, there's still a brief, spectacular peak in brightness, when the nebula is at just the right density, to catch and re-emit the star's light in its full shimmering spectrum. That peak is approaching now, and you're right in the middle of it. The glow sharpens around you, as if someone just turned up the cosmic dimmer switch to its brightest setting. Every filament, every wisp of gas now seems to stand out with impossible clarity. You can trace the arcs of ionized hydrogen, deep, crimson ribbons, curving like slow-motion fireworks. Between them, the turquoise glimmers of doubly ionized oxygen flash cool against the warm reds, creating a color contrast so vivid it feels almost painted by hand. Mainstream fact: this is the planetary nebula's brightness peak, when the shell's density is just right to catch and scatter the ultraviolet light pouring from the core. At this stage, the nebula can outshine entire clusters of stars, if you're lucky enough to catch it from the right angle and distance. Quirky tidbit: amateur astronomers sometimes call these peak brightness nebulae cosmic jellyfish, not because they float in water, obviously, but because their tendrils of glowing gas look like they could drift and pulse with a life of their own. Some even swear that through certain filters, they seem to shimmer, though that's more likely your brain playing tricks than the nebula wiggling for real. Astronomers still argue whether the intricate shapes you see, rings, butterfly wings, hourglasses, are entirely caused by the dying star's wind patterns, or if hidden companions, smaller stars or planets, are sculpting the flow. Binary interactions are tricky to confirm from light years away, so for now, the nebula's architecture remains partly a mystery. You drift closer to a section where the gas forms a thin arc, like the edge of a breaking wave. Along its surface, knots of dust look like dark freckles against the glowing background. Occasionally, a burst of faster-moving gas streams outward, slicing through the slower shell, leftovers from the star's last irregular outbursts before. It settled into its final shedding. The white-hot core is still a ferocious beacon at the center. It no longer swells and contracts. It's now a compact object barely the size of Earth, but with a mass half that of the sun. Imagine squeezing an elephant into a teacup and you're still not even close. The gravity it exerts is crushing, literally, holding its dense carbon-oxygen interior together against further collapse. Yet even here, in this strange glowing cemetery for stars, there's a whisper of renewal. That dust drifting outward will one day be part of new molecular clouds. Somewhere in the far, far future, those clouds may collapse again, igniting into newborn suns. You think of it like the cosmic version of composting. Nothing truly disappears. It just gets reused for something unexpected. You notice faint ripples in the gas, like gentle waves rolling away from the center. They're the echoes of the stars, earlier thermal pulses frozen into the fabric of the nebula. If you could speed up time, you'd watch them race outward, carrying the memory of the stars' dying rhythms. Farther out still, the gas fades into the interstellar medium. Here the density drops so low that even the ultraviolet light can't make it shine. Beyond that, there's just darkness, a deep, velvet black void peppered with the faint glimmer of background stars. This glowing shell you're inside is tiny compared to the galaxy as a whole, and yet it feels enormous when you're floating inside it. The colors around you start to shift subtly, a sign that the gas is thinning faster than the star can ionize it. You can almost sense the inevitable dimming, like the slow cooling of embers after a bonfire. In a few thousand years, this dazzling show will be over, and future travelers, if any, will see only a faint, ghostly ring or nothing at all. For now, though, you're here at the moment of greatest brilliance. The light is rich but not harsh, and the gas moves with such stately slowness that you could believe you're frozen in time. In the silence, the only thing to hear is the gentle hum of your own thoughts and the faint imagined hiss of photons meeting dust. From somewhere far behind you, a streak of motion catches your eye. A small, cold rock, maybe once part of a planet or moon that orbited this star, drifts quietly through the glowing shell. It doesn't shine. It simply passes through the light, indifferent to the spectacle. You wonder if that rock once felt the warmth of this star in its prime. You're close enough to the core now to feel, not heat exactly, but the oppressive presence of its gravity, tugging gently at your path. The star's death might be beautiful, but it's also inescapably final. Soon it will shrink into the quiet ember of a white dwarf, the gas will vanish into the galactic night, and the story of this star will be over, almost, because there's one more act left to witness. The core gleams ahead like a stubborn coal in the ashes of a burned-out fire. Its light is bluish now, harsher than before, as if it's decided that if it can't be big and flashy anymore, it might as well go for intimidating ice-cold glow. You drift closer, and the surrounding gas fades from view until all that remains is this small, impossibly dense jewel suspended in space. Mainstream fact: you're looking at a white dwarf, the final stable remnant of a medium-mass star. No longer fuses elements in its core. Instead, it shines from the residual heat trapped in its compressed carbon-oxygen interior. Its surface temperature can exceed 100,000 Kelvin at birth, but with no fusion to replenish that energy, it will slowly cool over billions of years. Quirky tidbit: the pressure holding the white dwarf up against gravity, electron degeneracy pressure, is basically the universe's way of saying, nope, you can't cram those electrons any closer together. Physicists sometimes joke that a white dwarf is made of the rules of quantum mechanics, which sounds cool until you realize it's not metaphorical, it's literal. Astronomers still argue whether some white dwarfs can explode in mini supernovae, called IA events, short bursts that would briefly reignite their brightness. It's rare, unconfirmed in many cases, and mostly theoretical. But the idea of this quiet ember suddenly pulling a dramatic encore is enough to keep sky watchers on their toes. you notice how incredibly small it is. This whole remnant is about the size of Earth, yet it contains roughly half the Sun's mass. If you could scoop up a teaspoon of its matter, it would weigh as much as an elephant, although good luck finding a spoon that could handle that. The surface gravity is so intense that if you dropped something, it would slam into the star at thousands of kilometers per second. No gentle thud here, more like instant plasma. Hovering near it, you see faint ripples of light shimmering across its surface, almost like heat mirages on asphalt. These aren't flames, but convection patterns and magnetic field interactions, twisting and shaping the thin outer atmosphere. Occasionally, tiny flares of ionized gas leap from the surface, not enough to create solar winds like the sun's, but enough to remind you that this isn't quite a dead object, it's just retired. Around the star, debris still drifts, a faint disk of dust and rock that may once have been planets, moons, and asteroids. Some of these chunks are spiraling inward, torn apart by tidal forces before being swallowed into the white dwarf's atmosphere. When that happens, the surface briefly flashes in a different spectrum, as if burping up the memory of its old companions. In C, the far distance, the last of the planetary nebula's gas glows faintly, now spread thin enough that the light of other stars begins to outshine it. The white dwarf sits alone, a cosmic relic, cooling so slowly that you could watch for 1,000 lifetimes without seeing much change. The thing is, you can't help but feel a strange affection for it. This little remnant has been through the drama, birth in a nebula, a youth of furious fusion, middle-aged stability, a swollen red giant phase, and a spectacular final shedding of layers. Now it's just here. Quiet. Constant. Waiting for time to do what time always does. You float closer still, and a peculiar thought slips in. Somewhere out there, civilizations might be orbiting other white dwarfs, basking in the leftover glow. Theoretically, a planet at the right distance could host life for billions of years during the cooling phase. It would be a dim twilight world, but it could be home. And yet, in the scope of the universe, even this final phase isn't forever. Billions, maybe trillions, of years from now, it will cool so much that it stops shining entirely. No light, no heat, just a cold, solid chunk of carbon and oxygen, a black dwarf. None exist yet because the universe isn't old enough. You're looking at a stage of stellar life that, in cosmic terms, is still young. That thought is both comforting and unsettling. Comforting because it means stars like this will shine for a long time yet. Unsettling because you've just been reminded that even the quietest cosmic objects have an expiration date. The white dwarf doesn't care. It doesn't need to. It simply exists, radiating away its heat into the cold void like the last ember, in a fire that no one is tending anymore. And here you are, drifting beside it, aware that the next step is one you'll have to imagine. Because it's going to take longer than the age of the current universe to see it happen. You stay with the white dwarf longer than you meant to, watching that slow, imperceptible dimming. But eventually, the pull of curiosity draws you forward in time, past billions of years, until the light finally winks out. At first, you think it's simply too faint to see, but no, it's gone. What hangs before you now is something the current universe has never produced in reality. Mainstream fact. You're gazing at what astronomers call a black dwarf, a purely theoretical object. It's the ultimate end state for stars. Like the sun, a body that's cooled so completely it no longer emits any measurable heat or light. It's not black like a hole. It's more like the color of forgetting, a perfect absence in the middle of space. Quirky tidbit. Scientists sometimes joke that black dwarfs will be the universe's cosmic paperweights, just endlessly sitting there. But the fun stops when you learn that after unimaginable spans of time, think numbers so big they make your calculator weep, Some of them might spontaneously explode due to quantum tunneling effects. That's the cosmos for you. Even your final resting state might get evicted. Physicists still argue whether these black dwarfs will ever form at all in the practical sense, because the timescales are so ridiculously long, on the order of 10-15 years, that protons themselves might decay before any star has time to cool completely. It's the sort of debate where you imagine the universe tapping its watch and saying, "You're seriously still waiting for this?" You run your hand, well, your imaginary cosmic tourist hand, over its invisible surface. The gravity is still crushing. Its mass hasn't changed, only its energy output. You know intellectually that it's still the same Earth-sized lump of exotic matter it's been since it was a white dwarf. But without light, without heat, it feels like you're standing next to a tombstone for an entire solar system. You take a step back and notice the silence. Sure, space has no sound in the normal sense, but there's usually something. The hiss of solar wind particles, the hum of background radiation, the faint static of a nearby nebula. Here, nothing. The space around a black dwarf is pure stillness, broken only by the faint ripple of dark matter passing through everything unnoticed. And yet, the universe is far from empty. Around you, other points of faint light glimmer in the far distance. Red dwarfs still burning slowly, neutron stars spinning their lighthouses of radiation, the occasional black hole patiently pulling in stray gas. Time feels thicker here, as if the seconds themselves have gained weight. You remember how bright this star once was, how its light could have nourished life on some warm little world. And now, this is all that remains. It's not sad in the way you expect, it's more inevitable. Like closing a book after a story has been told in full. You can't stay stuck in the happy chapter forever. Moving around it, you notice tiny, meteor-like specks drifting in slow orbits. These are the leftover fragments of its planetary system, asteroids and comets that never fell in, now circling a star that no longer shines. Their surfaces are frozen hard as diamond, covered in layers of ice that have been stable for billions of years. No melting here, no sunlight to stir them. A stray thought hits you. If some alien archaeologists far in the future ever found this black dwarf, they could piece together its history from those frozen rocks, like reading carbon-dated fossils. Every chemical ratio would tell the tale of what this system once was. In a way, the black dwarf is a sealed time capsule, keeping secrets in silence. You linger just a little longer, trying to see something, anything, reflecting off its surface. But it's hopeless. It's as if space itself has folded around, erasing any evidence of its presence. You only know it's there because you can feel its gravity tug at you in a steady, patient way, as if it's saying, "I'm not gone, just quiet." And then, because this is the kind of trip where time bends to your whim, you zoom out, way out, until this black dwarf is just one of countless other frozen corpses dotting the darkness. The living, fiery universe you started in is now just a distant memory, replaced by an era where most stars have burnt out and the cosmos has grown cold. It's not the end of everything, not yet, but it's the end of this star's story. And you were here for every chapter. You drift further into the darkness, your eyes adjusting to the new kind of universe that surrounds you. The stars you once knew, the glittering river of the Milky Way, the crowded constellations, are rare now. What remains are faint embers, the oldest red dwarfs, stubbornly sipping their fuel, casting a dim, wine-colored glow across the void. Everything feels slower. Not just the orbits of distant worlds, but even the sense of time itself, as though the ticking clock of the cosmos has been wrapped in heavy cloth. Mainstream fact. This is what cosmologists call the degenerate era of the universe. It's a time when almost all nuclear fusion has ceased, and the cosmos is powered mostly by the slow decay of matter itself. Galaxies have long since lost their shape, their stars flung into the darkness by countless gravitational encounters. You could wander for millions of light years between places where anything at all happens. Quirky tidbit. Some physicists describe this as the ultimate introvert's paradise. No neighbors, no noise, no invitations, just endless personal space. Of course, the downside is the nearest coffee shop is about 10 trillion light years away. Astrophysicists still argue whether intelligent life could survive this deep into cosmic time. Some suggest highly advanced civilizations might harness black holes for energy, extracting every last usable watt from their slow evaporation. Others think that no matter how clever you are, the math wins eventually, and the universe slips beyond the reach of anything resembling life. You pass the occasional black hole, their presence marked only by the way they bend the starlight from far behind. Some are ancient, primordial even, still slowly evaporating via Hawking radiation. They'll be the last fireworks of the cosmos, popping out of existence one by one over unimaginable spans of time. Eventually, you sense the faint hiss of the cosmic microwave background, now stretched to absurd wavelengths, colder than a whisper. Even light has grown tired here, photons diluted across an expanding space so vast, you can't quite wrap your mind around it. As you float, your mind flickers back to the nursery of stars you saw at the beginning of this journey. The glowing dust clouds, the infant suns. Compared to this silent epic, it feels like remembering a bustling city in your childhood. Everything alive, everything moving. And now, just the last candles burning in an infinite hall. The black dwarfs you saw earlier still exist here, even colder now. If you touched one, not that you could, you'd feel something closer to absolute zero than anything nature ever made in the early universe. They sit, patient as mountains, waiting for the quantum instability that will one day unmake them. There's no rush. The universe has mastered the art of waiting. You notice with a strange comfort that despite the emptiness, there's still a kind of order. Gravity still works. Physics still follows its rules. The dance just has fewer dancers now, and the music is slower, deeper, almost imperceptible. At some point, though you can't tell if it's been seconds or a billion years, you realize you've reached the true horizon of the star's story. No more transformations, no more light, no more warmth. The matter that once burned bright is now dust, drifting toward an end so far away it almost doesn't matter. And here, finally, the narrative quiets. The black holes will fade. The dwarfs will explode or dissolve. The particles will thin out, until the universe is just a cool, dark soup, expanding forever into nothing. And somewhere in that darkness, if the laws of physics permit, maybe, just maybe, a fluctuation will spark something new. But that's another bedtime story. For now, you let go, letting the quiet seep into you. The journey has been long. You've seen birth, life, death, and afterlife. You've drifted alongside fire and ice, watched whole worlds form and vanish, felt the weight of time on a scale too vast for human thought. And now, the story is over. And here, as the darkness stretches endlessly in every direction, you feel your own breathing slow. There's no rush here, no urgency. The stars have finished their work. The galaxies have gone quiet, and the universe has settled into a deep, dreamless rest. You're just a small passenger in this vast stillness, floating weightless among the last traces of what once was. Every moment feels longer now, each second stretching into something soft and almost shapeless. There are no harsh lights, no sharp edges, only the muted glow of memory and the gentle pull of invisible forces guiding you onward. You drift past the remnants of countless stories, each one folded neatly into the fabric of space-time, and you realize that even endings can be beautiful. Your thoughts grow lighter, slower, The images of brilliant nebulae, blazing suns, and collapsing giants fade into a warm blur at the edges of your mind. You remember the quiet laughter of the universe's stranger moments, the quirky facts, the odd debates, and they too become soft, like pages closing one by one. It's not silence you feel now, but something deeper, a kind of cosmic exhale. The universe isn't gone, it's simply resting, and so can you. Let yourself sink into that quiet. Let the immensity of time and space cradle you, knowing that in the grand, endless story of the cosmos, this is just one chapter, and your own is still being written. Close your eyes. Drift. Let the last glimmers fade into the black, and know that in the stillness there is peace. Sweet dreams.